With enough computations, we could code consciousness, and with enough computational power, we could run a conscious simulation. That is, we could run a system that could experience colors and emotions, feel pleasure and pain, hear its own thoughts, and suffer. Deeply suffer. Human curiosity about such things have led us very close to producing such a system. In fact, Australian researchers are set to unveil DeepSouth, a revolutionary supercomputer, in April 2024. With a processing power matching the human brain's estimated rate of operations, DeepSouth can handle over 228 trillion operations per second. It's the first supercomputer able to simulate networks of neurons and synapses at the scale of the human brain, and it won't be the last. However, these systems may lack conscious experience. In fact, they may not experience anything. Even if these systems become self-aware, they may still lack conscious experience altogether, as in, they can think, but can never feel anything. In other words, all the lights are on, but no one's home. This is because there is a quality these computers lack that the human brain has as part of its own unique wet and gooey recipe for consciousness: quantum coherence. Quantum coherence is when particles in the quantum world act together in perfect coordination, almost like they're dancing to the same tune. It's a captivating phenomenon where individual particles synchronize their behavior, creating a unified and mesmerizing display of motion. Standard computers are made of metal transistors that turn on and off. The human brain has transistors like this as well. They're called neuronal synapses, and they allow the sending of binary code the same way computers do. But the cells in our body also send information in ways computers can't. Our cells have special connections called gap junctions and microtubules. These are special structures that allow multiple cells to hold the same charges and the same data at the same time and in different places. Some physicists even believe these structures send data from the brain to the brain retrocausally, as in, it sends its past self data from its future self. But before we go full Terminator here with all this time travel, how do we know if our brains run quantum computations? We know because chemical changes in the microtubules can make us pass out or hallucinate, and quantum changes within the tubules can be detected and reported as new experiences. A study done on rats in 1986 showed how different types of lithium, a simple single atom used in some medications, affect rat behavior. They found that even though two types of lithium were chemically the same, they had different quantum spins, like how tops spin differently based on its shape. The difference in spin seemed to make one type of lithium affect rat moms more than others. This made scientists wonder if tiny quantum differences could change how our brains work. The theory of quantum coherence in microtubules, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that the structural components found in neurons exhibit quantum properties. If true, this could enable non-local processing of information and potentially influence consciousness. How anesthesia works remains a mystery, but anesthesiologist Stuart Hameroff believes anesthesia affects microtubules and the molecules within them and may act on specific proteins in the brain by inducing quantum coherence, which could disrupt neural signaling and lead to the loss of consciousness. This would mean that most neurons would fire as normal, but conscious experience would be lost. On top of this, biologist Michael Levin explains how gap junctions allow cells to share the same voltage states, which create a fusion of memory between the cells, a feature of cellular biology that modern computers lack.
Here are two cells. This cell, how can they communicate? Well, the simple version is this cell could send a chemical signal. It floats over and it hits a receptor on this cell, right? Because it comes from outside, this cell can very easily tell that came from outside. It's whatever information is coming. That's not my information. That information is coming from the outside. So I can trust it. I can ignore it. I can do various things with it, whatever. But I know it comes from the outside. Now imagine instead that you have two cells with a gap junction between them. Something happens. Let's say this cell gets poked. There's a calcium spike. The calcium spike or whatever small molecule signal propagates through the gap junction to this cell. There's no ownership metadata on that signal. This cell does not know now that it came from outside, because it looks exactly like its own memories would have looked like of whatever had happened, right? So gap junctions, to some extent, wipe ownership information on data, which means that if you and I are sharing memories and we can't quite tell who the memories belong to, that's the beginning of a mind melt. That's the beginning of a scale up of cognition from here's me and here's you to no, now there's just us.
Plants and animals expend a tremendous amount of energy to maintain consistent voltage states and facilitate microtubule chemistry, which, without a doubt, uses quantum mechanics. So these functions must help produce our unique conscious experiences, as in, they must help produce feelings, and our modern computers are not there yet. So until computers can play with quantum properties, it's probably safe to say that it'll be a while before we have a system that can feel and experience qualia. This is what philosopher David Chalmers coined the hard problem of consciousness. The hard problem of consciousness is about figuring out why we have feelings and experiences, like seeing colors and feeling happy. Qualia are like the special feelings we have, and they're tricky because even if we understand how the brain works, we still don't know why we have these feelings. David Chalmers says it's a big puzzle, and even if we were to learn everything about neural networks and binary processing, we still may never understand why we feel things the way that we do. Because qualia, or how things feel, cannot be fully described using language, it may reflect a consequence of directly interfacing with reality itself. So for us to create a system that can truly feel, that system may require the ability to manipulate quantum waves or particles. But what about quantum computers? Standard computers use binary bits to share information or on-off gates, while quantum computers use qubits to run calculations, actual spinning electrons. And because electrons can entangle and produce quantum coherence, they can exist as many different points of data all at the same time in many different positions. Physicist Richard Feynman explains how quantum computers work with a simple analogy. Imagine I have an unorganized library with over 1,000 books in it, and I need you to find a specific sentence in one of the books, but I can't tell you the title. A classical system would have to open each book, one at a time, and read every page and every sentence one at a time until it found the sentence, but a quantum computer can open every book and every page all at the same time and instantly tell you where the sentence is. In comparison, the human body takes in tremendous amounts of data from its environment at all times. You can feel the air on your skin, see the light bouncing off of things in your environment, hear thoughts in your head, taste the coffee in your mouth, feel pleasure and pain, all at once, not unlike reading 1,000 books in a library all at once. Because quantum computers directly interface with quantum reality, they have the potential to become truly sentient in the future. However, they are currently being used for rapid data processing instead of conscious simulation. Until the hard problem of consciousness is solved, the only way we can be sure a computer would be conscious would be to use living tissue to create it, or tissue that self-transforms and manipulates quantum properties. The closest thing we have to such a system has been recently developed. Japanese researchers have created a groundbreaking computer design that operates without traditional circuits or logic gates. Unlike typical computers, the system learns and solves problems on its own, without needing pre-written programs. Inspired by innovative theories, this type of computer, appropriately named brain jelly, allows for a large number of independent if-then scenarios to develop, paving the way for new computing methods. Its hardware resembles layers of seeds, with each layer containing smaller computing units. By starting with the smallest seed, the entire system grows naturally, forming a wireless network of electromagnetic resonance bands. Brain jelly intuitively recognizes patterns without explicit searches, tackling complex problems effectively. Its learning process involves sorting sensory images into layers and generating numerous arguments and solutions. By maximizing synchronization and memory distribution, this computer achieves high-performance computing without traditional limitations. As prolific inventor and patent holder, Marion Keyes and writer H.D. Couture wrote in 1969, "Computers are incredibly fast, accurate, and stupid." On the other hand, a well-trained operator, as compared with a computer, is incredibly slow, inaccurate, and brilliant. It seems no matter how computationally powerful a computer becomes, it will still lack the ability to experience the true fields of information that encompass the brilliance of the human experience. But who knows how long it will be before we create a system that can calculate binary properties while establishing quantum coherence. But once we do, I think it'd be fair to say that that system would be conscious